Greetings, welcome to my lecture series on basic circuit theory. I am Razavi. Today, in this first lecture, we will begin with the following question: why circuits? I would like to provide some motivation for our study of circuits in this course. Then I will go over the contents of what we will be covering in the next 40 to 45 lectures and look at the outline. And finally, we will jump into the material and talk about electric quantities. All right, so we should really start by asking this question: why circuits? What is the significance of circuits in our daily lives? Well, I will answer this question with two questions. Question number one, haven't circuits been around for a very long time? Yes, indeed, they've been around for more than 100 years. Question number two, have we invented every circuit that can be invented? The answer is absolutely not. Every year we see new circuits come to life. Why? Why do people create new circuits? Because they are responding to emerging applications, to applications that demand a higher performance and hence require innovations in circuit and system design. So just to give you a few examples of interesting situations where circuits and circuit theory come to our aid, let's go over to this screen here and look at a few cases. All right, so we're going to start with this paper. This paper deals with monitoring of glucose in our blood. If you know anyone with diabetes, you have probably seen that they have to poke their finger and draw blood before every time they eat, before they have a meal. They have to measure the glucose in their blood. And it's a very painful process because they have to draw blood from their finger twice or three times a day. So if we have a means of monitoring the glucose non-invasively, meaning without drawing blood from our body, then it is a great invention. And this paper deals with that idea. So we want to monitor the glucose in the blood without actually drawing blood. And they have created this circuit, which you can see consists of a bunch of inductors and capacitors and resistors. And these are built on this printed circuit board. So to measure the glucose in my blood, I will place my finger on top of this printed circuit board, and the level of glucose in my blood changes the values of some of these components, in particular some of these capacitors. So from that change in the capacitance, we can tell how much glucose I have in my blood. So it's a beautiful invention. It has no invasion of the body in terms of drawing blood, and it can measure the glucose in a very simple and nice format. Okay, next I would like to talk about our premier conference, the International Solid-State Circuits Conference, which draws about 3,000 people every year. So why do 3,000 people go to this conference to learn about circuits? These are from academia and industry. Well, because there's demand for new applications and new circuit techniques. So I would like to show you a few circuit techniques from this conference in recent years. So here's one. This is a paper from this company, and we don't worry about the title of paper right now because it may not make much sense. But if you look at the circuit, which is called the receiver front end, and it's a new circuit, we might identify certain components. We have inductors, we have capacitors and resistors, and some other devices that we may not recognize. So indeed, everything that we will learn in this course proves useful in cases like this. Here's another example from 2021, a paper by one of my students. And again, this paper, he is proposing certain new circuit topologies. And you can still see some of these components, right? You can see inductors and resistors and capacitors, and then some other devices. So all of these are necessary to provide a higher performance for certain applications. And as we go through this course, I will show you more and more examples of how circuits and electronics become interesting and useful in our daily lives. All right, so let's begin with the course outline and see how we want to proceed. We're going to start with electric quantities and devices. So electric quantities include charge and current and voltage, etc. And then electric devices include voltage sources, current sources, resistors, capacitors, and many other components. So electric devices. Okay, it makes sense, right? Because if you're going to build a circuit, first we have to understand what quantities in that circuit are of interest to us. And then we have to understand how the devices that comprise the circuit behave. How do we model these devices? What equations can we write for these devices? And then we can start building circuits and in particular look at laws that govern the behavior of circuits. These are Kirchhoff's laws, which you might have seen in physics before. Okay, so with this knowledge, we should be able to analyze any circuit. We don't need anything else. But as the circuits become more complex, we need better tools, shortcuts to analyze these circuits. And also we need to gain insight. It becomes more difficult to intuitively understand how the circuits operate. So in that respect, we will introduce other concepts, for example, analysis techniques. And the purpose of these techniques is to provide a systematic and methodical approach to analyzing circuits so that it becomes more of a mechanical operation. We can have a procedure to follow and analyze any given circuit that we have. And then we also go over some circuit theorems that further simplify the analysis. Through these theorems, we can readily look at a circuit and predict what it will do or what parts of it will do. So these together, along with the basic fundamentals that we have learned, allow us to handle pretty much any circuit that we have. All right, and then hopefully we will have time after this. We will look at RC, RL, and RLC circuits. Again, you might have seen some of these in the past in your physics courses, but we will go through them and analyze them one by one. And finally, if we have time, we will look at op-amp circuits. So op-amp circuits. You may not have heard of op-amps. Op-amp stands for operational amplifier, and op-amp is a useful device with which we can build interesting circuits. So we'll try to address some of these as well. All right, so before we begin studying any of these concepts, I need to refer you to this the simple theorem that we have, Ohm's law. I hope you have seen this before. Ohm's law says that if we have a resistor of value R and we pass a current through it equal to I, then this resistor will have a voltage across it that is equal to IR. So we often refer to this even today because it allows us to study various examples. All right, so with all of these, now we are ready to jump into the material and start with electric quantities. We will study three quantities, actually really two quantities here, that will be extensively used in everything that we do. So we should have a nice definition and a clear understanding of these quantities as we go along. All right, so the first one is charge, which we usually denote by Q, and its unit is in coulombs. The unit is coulomb, and it's also shown by uppercase C. So what is charge exactly? Well, we don't really know. Charge is a property that we attribute to elementary particles, such as electrons and protons. And we sort of say, okay, electrons have negative charge and protons have positive charge. What charge is, we really don't know. It's just a model that we have, it's an abstraction that we have that helps us explain the behavior of these particles. All right? So we just leave it at that. We just assume that, yes, some particles have negative charge, some particles have positive charge. But more of interest to us is actually when the charge begins to move, because that creates a current. So the next quantity that we study, and we study more carefully, is current. So we say current occurs when electric charge moves. Okay, and it makes sense. If we look at a water analogy, we can see that clearly. If you have a pipe of water, so here's a pipe, and we have water passing through it, so H2O. So we have water molecules passing through the pipe. That gives us a current of water. Similarly, if we have a wire and we have charge passing through it, that gives us a current of electricity. So we see the similarity between the two situations. All right, so that's great. Intuitively, it makes sense. But then how do we exactly define the current? Or how do we calculate the current passing through a wire or a branch in a circuit? All right, so what we are thinking is the following. So we say that the current passing through this wire is equal to, I'm going to sit in this wire and look at the charge that's passing through the wire. So I sit there for some amount of time. So let's call that amount of time T. So we sit in the wire for T seconds. This pen sometimes acts up. So we sit at this wire for T seconds and calculate how much charge is passing through it, and we denote that charge by Q. And we say the total charge that passes through the wire in T seconds is defined as the current. But that definition actually is not very good because it can run into problems sometimes. So let's put a question mark here. All right, so for example, how do I choose this T? You say, okay, why don't we pick T to be 1 second? So we sit here for 1 second, look at the charge that passes in 1 second, and divide that charge by 1 second. That gives us the current. Well, but what if the system is not even operational for 1 second? For example, if you have a Wi-Fi system, the Wi-Fi transmitter or receiver turns on and off every, for example, 1 millisecond. So if you look at any wire in that system, that wire does not even have charge through it for 1 second. The observational window that we have has to be less than, for example, 1 millisecond. So then the question is, how do I choose T so that I have a universal definition for the current? So it makes sense to make this T really, really small. So if you make it really, really small, then the situation is as follows. We say the official definition of current is we go to a very small amount of time And during that small amount of time, we have some amount of charge. And that amount of charge over that amount of time gives us the current. So the official definition of current is to find the rate at which the charge passes through this wire, so dq over dt. The unit of current is amperes, so we denote it by capital A, and that's what we use to measure the current. All right, so that's the definition that we have, and that's the intuition that we have behind it. Now let's make a few important observations about the current. So important points. So number one, every current that we have in any circuit, in any branch, is characterized by two quantities. Okay, so I have to remember that. So we say each current has a value and a direction. So we must not forget the direction of the current. So for example, we say this current is equal to I1. That means that the value of the current is I1 amperes, and the direction of the current is this way. Or you could put the arrow the other way. It's up to you, but we have to always use an arrow to indicate the direction of the current. Okay, point number two. Let's see, I want to make sure that I am following all of these carefully. All right, so an open circuit guarantees I equals 0. So open circuit means what? Means, for example, I have a piece of wire and I break it, right? So there's a break between these two. There's an open circuit. And now we don't have any path for the charge to flow from here to here. If there's no path, there's no current, right? So we say that this current is guaranteed to be 0. So that's all we can say when we have an open circuit. This seems trivial right now, but it will become more complicated later. How much is the voltage difference from here to here? We don't know. An open circuit only guarantees a 0 current, but it knows nothing about the voltage from here to here. That voltage is given by the circuitry surrounding this open circuit. All right, just keep that in mind. Okay, let's see. Then we have the third point, and that relates to the amount of charge. So if I have a current through a wire and I'm asked to calculate the charge that passes through the wire in a certain amount of time, how do I do that? Well, I just have to work from here, right? So we say the amount of charge passing through a wire or a branch in a certain time t1 is given by the following. Okay, so I have the current, I need to find the charge. So I have to integrate the current with respect to time. So I say Q is equal to integral of the current with respect to time from 0 to t1 to this time. So we can go back and forth. We can go from current to charge, or we can go from charge to current, depending on what the situation is. All right, so these were some important points that we need to keep in mind. Okay, let's go over some examples to just drive these concepts home. So we're going to start with this example here. Let's see if I can find a another color here. Okay. So, all right, so the example I have looks like this. We have measured the current through a resistor to be like this, I as a function of time. We see that the current is 0 up to some time t1, and then it jumps to some value, which we call I1, stays at that value, then jumps back to 0 at time t2. Okay, so this is the current through a resistor. All right. Okay, and now we are asked to compute the total charge that passes through the resistor after this point in time. All right, after all of this is finished. Okay, so we say Q is equal to integral of the current is 0 here, so we don't have any integration there. 0 here, so we just integrate from t1 to t2, and it's just a constant value. So we say I1 dt from t1 to t2, and that's just t2 minus t1 times I1. All right, so that's a simple situation. But what this tells us is that, yes, as expected, the charge is actually the area under the current plot, right? You plot the current as a function of time, and we find the area under that plot, that would be the charge from any time to any time. Okay, all right. So let's look at another example, and this time we will want to do the following. So construct a circuit that creates this current. So this current. So I would like to build a very simple circuit that does this. It creates a current that has this dependence upon time. All right? So this is the quiz of the day. I will give you 1 minute to think about it. All right? All right, so what did you get for the circuit? Well, we are essentially synthesizing a circuit that performs this function. Okay, well, what we can imagine is that we have some sort of battery. Well, we need some sort of battery to create a current, right? So let's suppose we have a battery whose value is VB. So that will be, let's see if this pen cooperates. Okay, VB. All right. This battery is connected to a switch and to a resistor. Let's call that resistor R1. And this switch closes or turns on at time t1. Before T1, it's open, it's not conducting. If it's not conducting, this resistor doesn't see any voltage across it. This part of the circuit is not connected to this part, so the current through this resistor is 0. So I will call this current I, and I'm hoping that this I will behave as shown here. All right, at time T1, we turn the switch on, meaning we close it. So it turns on like this. We say at time T1, this is the notation we use. This arrow means the switch is turning on, is closing at time T1. So at time T1, we have a voltage of VB across the resistor. And Ohm's law tells us that the current through the resistor will be the voltage divided by the resistor. So we see that I now becomes equal to VB over R1. And all I need to do is choose VB over R1 to be equal to this value. And this continues for a while until time T2. At time T2, the switch opens or turns off again, and that brings back the current to 0. So we see that a very simple circuit like this can give us that type of waveform for the current. Okay, so with that, now we are ready to go over to our next electric quantity. So we talked about charge and current. The next quantity will be voltage. So let's talk about voltage and see how that comes about. I'm going to go to the next page here and see what we can do. Okay, so let's talk about the next quantity, which is voltage. All right, you have seen the concept of voltage in physics probably. Sometimes there you have called it the potential difference. We call it voltage difference. It's the same thing. And we know that the unit of voltage is volts. So we can measure it in that. But exactly what is the definition of voltage? What is the definition of voltage difference? Okay, so suppose that I have a point here and a point here. So we call this A, we call this B. Okay? And someone says measure the voltage difference between A and B. So A and B could be in some big circuit somewhere, right? We have various nodes and branches and so on. Here's a big circuit, and someone says find VA minus VB for me. Okay, so that's the voltage difference between A and B. All right, so this voltage difference is defined as follows. We will take a unit positive charge. Okay, so let's change the color here to blue. We'll take a unit positive charge, so plus 1 coulomb. Okay, so this is Q. From this node, and we will carry it up to this node. Okay, so we'll carry it up to this node. We take it from node B to node A. And in this process, we will probably do work on the charge. We have to push the charge up to go from B to A. So the amount of work that we do, the amount of energy that we spend in carrying the charge from point B to point A is called the voltage difference between A and B, provided that the charge has a value of 1 coulomb. Okay? So we're going to write this as the amount of energy necessary to take a positive unit, so it has to be positive and it has to be units. A positive unit charge from B to A. All right, that's our official definition of the voltage difference between A and B. So we can either start with a charge of 1 coulomb and then find the energy. That energy would be the voltage difference in volts. Or we can start with some general charge, some general positive charge Q, and then find the amount of energy and then divide that energy by Q. And normalize it to Q. However you want to do it, but that's the concept of voltage difference between 2 points. All right. Another example that I can offer here is something like this. Suppose we take a conductive plate like this. So big piece of metal, a big piece of metal plate up here, another big piece of metal plate down here. All right, so we take another one down here, and we connect a battery between these 2 plates. All right, so as you remember from physics, we have some, this battery gives us some positive charge on this plate, some negative charge on this plate, and it creates an electric field from here to here. So we have an electric field oriented in this direction. Now, to measure the voltage difference between these 2 plates, which actually is this voltage, right? To measure the voltage difference between these 2, I will perform that experiment. I will take some amount of charge. So let's go to a different color, maybe green. I take some amount of charge, so for example, +1 coulomb, and try to bring it from this plate to that plate. So now you can see that I have to do work. Why? Because I'm pushing a positive charge against the field. So I have to push it, I have to, as if I'm lifting it, right? So I have to push it up to bring it up here, and then the voltage difference, VB, between here and here, this voltage, will be equal to the energy that is necessary to bring this to the other side. So energy needed to bring charge from lower plate to upper plate. Okay, so you can see that these 2 are really the same thing. This gives us a more physical, more intuitive picture of what the voltage difference means. All right, so now that we have learned the concept of voltage, we're going to go over some important points. So important points. So number 1. So just like the current, which had a value and a direction, the voltage always has a value and a sign. So a voltage has a value and a sign. So here are some examples. We have a resistor. We say there's a voltage of V1 across this resistor, V1 volts, so 5 volts, 2 volts, right? But we also must specify the sign of this voltage. For example, we say the voltage is positive here, negative here, meaning that this point is, for example, 1 volt higher than this point, right? V1 volts higher than this point. Or I can have something like this, in which case this means that this side is higher than this side by V2 volts. So we always have to have these 2 notations plus this value for any voltage that we specify anywhere in our circuits. Okay, point number 2. Voltage is meaningful only between 2 points. So whenever we say voltage, we really mean voltage difference. And what that means is that whenever I say the voltage at this point is 5 volts, what I'm really saying is that the voltage from this point to another point is 5 volts, right? We should always have 2 points between which we are measuring the voltage. These 2 points can be like this, they can be like this, they can be like this, and many other types that we will see. But we always have to remember that voltage is actually voltage difference between 2 nodes. All right, let's see if there's anything else that we want to add here. Yes. So a short circuit guarantees V equals 0. A short circuit means what? Just a piece of wire, a piece of really good wire that has no resistance, right? So if I short circuit 2 points, so let's say I had a point A, I had a point B, and I came along and I put a very good piece of wire between A and B. I shorted these two together. So what happens? Well, a short circuit guarantees that the voltage now from here to here is 0, right? This is a short circuit. We can see this from Ohm's law. Ohm's law says that V is equal to I times R. If R is 0, I picked a very good wire, so its resistance is very, very small, it's close to 0. If I have 0 resistance and I have any current less than infinity, then that resistance times that current always gives me a voltage that is equal to 0. Okay? So that's what the short circuit guarantees. The voltage difference from here to here is 0. What does the short circuit tell us about the current passing through this? Nothing. The current passing through this wire is given by the circuitry surrounding this short. So we know nothing about that current just by looking at this short circuit. That's the distinction between an open circuit and a short circuit. If you remember, the open circuit guarantees a 0 current. A short circuit guarantees a 0 voltage. All right. With that, we are now ready to go over some examples. Let's change the color here and look at some examples. Okay. One example that I have here is as follows. Suppose I have a battery like this, and I have a resistor like this, R1. This battery is VB, and I am interested in this voltage across the resistor. We call this V out. And there's a switch here, and this switch closes or turns on at t equals 0. So I would like to plot V out as a function of time. Okay, so that shouldn't be that hard. Before the switch closes, before the switch conducts, there's an open circuit here, right? When the switch is not conducting, no current can flow this way. If no current flows through R1, Ohm's law says R1 has no voltage across it. So V out is 0. So before t equals 0, the output voltage is 0. So let's try to sketch that here. So we have V out as a function of time, and before time 0, there's no current passing the switch is not conducting, it's off, it's open, so R1 sustains a 0 volt difference. At time 0, the switch begins to conduct, so it shorts this node to this node. A short guarantees that the voltage difference is 0. So the voltage across R1 is the same as the battery. You just connect the battery to a resistor, right? So the resistor now has VB volts across it. So V out, which is the voltage across the resistor, is also equal to the battery voltage. So this just jumps to VB. Okay, that seems simple and trivial. All right, very good. Okay, But now let's decide on one interesting twist to this circuit. Suppose I go and do the following. I have this battery, and I will connect a resistor from here to ground. Call this R2. All right? And I would like to repeat this experiment. I would like to plot V out as a function of time now that R2 is present in the circuit as well. How does V out change in this case? Well, when the switch is not conducting, there's no current through R1, V out is still 0, so not a problem. This is 0. When the switch begins to conduct, does the voltage across R1 still equal VB, or is it different? Okay, well, the switch begins to conduct, so it's a piece of wire. If it's a piece of wire, this voltage difference is VB, the battery voltage. This voltage is still VB. I have a battery, I have a resistor here, and I have one more resistor over here. They're all connected in parallel. So this is VB, this is VB, this is VB. Everything is still VB. So the voltage across R1 is still the same as before. So when I connected R2 in parallel with the battery voltage, nothing changed as far as these other voltages are concerned, because this battery wants to enforce its voltage across these two points. And it doesn't matter, anything we connect here cannot change this voltage because it's considered an ideal battery. So for an ideal battery, the voltage from here to here is always VB volts, for example, 1.5 volts, regardless of anything that we connect to it. So this voltage does not depend on R2. All right, this concludes our lecture today. I will see you next time.